the last video, we have discussed about the torque and the angular momentum of a single particle. Now we are going to discuss torque and angular momentum for a system of particles. So let's say we have a system of particles here. Let's say this is a system, and I'm drawing here coordinate axis. So let's say this is x-axis, this is y, and this is z-axis, and then let's say this is first particle in the system, the second particle, and up to n particle. Now, if we are randomly picking one particle, let's say this is ith particle in the system, and it has mass m and velocity vi. So I'm writing here for ith particle. Let's say it has mass, and consider all the particles are of same mass, means each particle has mass m. So for ith particle, mass is m and its velocity is vi. Then its momentum will be ei, linear momentum will be mass times velocity. And if the position vector for this ith particle is Ri, this is origin, Ri, then angular momentum for this particle can be defined as L equals to R cross linear momentum. So I am writing the index I for ith particle, and here I can vary from 1 to n. Means if I am putting I equals to 1, that is we are talking about this first particle, and so on. If I am putting I equals to n, we are talking about this nth particle. So this is angular momentum for ith particle, and if we want to know the angular momentum of the system, we have to sum this momentum, angular momentum of the particles, and this sum will be vector sum. How we can write here? Summation I equals to 1 to n, and L can be written as Ri cross Ei. So this is angular momentum of the system, and the system has n number of particles. Now what about torque? So let's go on. The torque can be defined as, for the system, this can be defined as the time derivative of this angular momentum, and then we will have this thing, and I equals to 1 to n and Ri cross Pi, and then we have, look, we can take this summation side outside, and it won't affect the result. So we can write it Ri cross Pi. This is what we can write for total momentum, total torque here, and this is for total momentum, including this sum sign. Okay, now we can write here summation I equals to 1 to n, and this is time derivative of angular momentum of ith particle. So we can write it torque of ith particle. Okay, let me make it little bit cleaner. So this will be torque of ith particle. So in this way, we can take the torque for this system equals to sum over I to n, and this is torque on ith particle. So individually, we can add this vector addition here. We can vectorly add all the individual torques on these particles. And now, let us continue. If we are saying that this torque equals to, as we have just obtained, I equals to 1 to n, and this is torque I, or we can write it summation. I'm not writing again and again this I equals to 1 to n. I'm just writing summation sign, and you should treat it as this. So torque on ith particle will be position vector of ith particle times force on ith particle. And now we know this force on ith particle will include external forces as well as internal forces. So Fi, let me write here ext for external, plus Fi internal. Why I have separated these two things here, you will soon come to know this thing. So Ri here, cross sign, Ri cross F on ith particle external plus summation Ri cross F on ith particle internal. And now we know if we are going to sum all the internal forces. So these forces we have already discussed. These forces occur in pair, and so the net force will be zero. So here this term is not going to contribute. So the torque will be, total torque will be the only external torque here. This is external torque. So these particles, whether they are interacting with each other in any manner, this thing is not going to give a net effect on its torque. Rather, the torque which is going to produce any effect is external torque. So we can continue this argument and we can write the rate of change of total angular momentum of the system is nothing but tau external. Now we are moving towards the conservation of angular momentum. So how can we say? Let's say there is zero external torque on the system, means this term is zero. In that case, what will happen? Let me make some space here. Okay, so in case in case this external torque is zero, then total angular momentum of the system will also zero, and this implies the angular momentum of the system is a constant, or it will remain conserved, as we have discussed this thing in case of translational motion where linear momentum was conserved in the absence of net external force. In the same way, you can say if there is no net external torque, the angular momentum of the system will remain unchanged or conserved. Okay, now let's take the component form of this thing. It means we can, if we are talking about in Cartesian system, we can resolve this angular momentum vector into its components along the three axes, and this will be Lx I cap Ly. This is component of angular momentum towards positive x direction, or let's say along I cap, and similarly we can write other components too. So this will be k cap. And now, as these three components are independent, these three components are along independent axes, so we can say that Lx, Ly, and Lz, these three may be different constants. So we can write something C1, something C2, or something C3. So keep these all things in mind. These things are helpful in solving numerical problems, not right now, but later in future. They are going to help you if you are going for higher studies. Okay, now let's go for a problem, means an example from your textbook. So let me bring that first. Okay, so here we have example 6.5. We have to find out torque due to force given in its component form, and we have to find out the torque about origin, and the force acting on a particle and position vector of that particle is given. So we need not to draw actually for this particular problem. We can just write the force acting is 7 I cap plus 3 j cap minus 5 k cap, and the position vector is I cap minus j cap plus k cap. And we know torque can be given as, here we are talking about a single particle, torque can be given as R cross F. So here we have tau equals to R cross F. And then we know this thing that we can write in determinant form, where R cross F can be given as, we have discussed this all things earlier. So this will be given as, now components of R here. So Rx is this much, coefficient of this I cap. So this will be 1. Similarly, Ry or y coordinate simply is -1, and this is 1. Now, what about Fx means x component of this force? This is 7, the magnitude of x component, and then 3 magnitude of y component of the force, and then minus 5. And now we can just solve this determinant to find out the answer. So how can we do that? So torque equals to, look, we have to take this thing first. So I cap, and then we have to eliminate this line, and this is its coefficient here. So minus 1 into minus 5 will give us 5, and then minus 3 into 1, that will be 3, and plus, and of course, second thing we have to write here minus instead of plus, or you can write minus, but order you need to change. So I am keeping it simple, just using alternative sign here. So then there will be minus sign, and then coefficient of j cap, and then plus sign, and then coefficient of k cap. So what is coefficient of j cap here? We have to calculate. So j cap is here. We have to eliminate this column and this row, and then we can write minus 1 into minus 5. That will be minus 5, and then 7 into 1, minus 7. This will be minus 12, and again here minus sign, that will give us 12. Okay, let me write it first, and then we can solve it. Then for k cap, it will be 3 into 1, that is 3, and minus 7 into 1, that will be minus 7, and minus of minus 7 will give us plus 7. So finally we have 2 I cap and plus 12 j cap plus 10 k cap, and we have directions also. So let's move to the next example. So we have example 6.6. Now we have to show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. So let's say we have a particle moving along this line, this straight line. Constant velocity means magnitude and direction both are not changing. So let's say this is particle moving along this line, and its velocity is v, and velocity is not changing. And if a vector quantity is not changing with time, it means it is keeping its magnitude as well as direction constant. And this is, let's say, position vector, and I have chosen a random point here, and about this point I want to find out its angular momentum. So okay, let me use this color only. This is r, random point, and position vector from this point is r, and let's say the angle between velocity vector and this position vector is theta. So, and mass of this particle is m. So angular momentum for this particle will be L equals to r cross p, which will be r p sine theta, and unit vector along the angular momentum. So let me first find out the unit vector. Where should it be, means in which direction the angular momentum should be. So here we can use that right hand rule, and r cross p, we have to curl the four fingers, placing them initially along this r vector, and afterwards we have to curl those fingers towards this. So if you are doing this using right hand, your thumb will indicate a vector pointing inward. Means if you are watching over screen, it is pointing inward, means into the screen, and we know that we can use special symbol here. This is vector pointing inward, and this symbol we use for a vector pointing outward. Yes, perpendicularly outward or perpendicularly inward, more precise here. So if this vector r and vector v is in the plane of this screen, the angular momentum vector will be along this direction. That is pointing inward into the screen. Okay, so we have sorted this thing, and as long as this vector is moving with constant speed, and this position vector is also lying in this plane only, so both r and v, and if I'm saying v, that is m times v also will lie in the same direction. So if these two are not changing direction, if these two are always lying in the plane, in this plane, the direction of this angular momentum will always remain along this only. So direction is not changing for this angular momentum. So one part we have done. Now what about this r magnitude part? L equals to r, and p is mv, and then sine theta. Now, mass is not changing, and if velocity is constant, this v is also not changing. Now we have to check about r and sine theta. So r is changing, and so sine theta. But one thing we can figure out here, r sine theta is the perpendicular distance. You can check here. If this is theta, this is vertically opposite angle theta, and if we are taking this perpendicular distance, this will be r sine theta. And as long as this particle is moving along this straight line, this perpendicular distance r sine theta is also a constant. So m is constant, v is constant, r sine theta is constant. That is magnitude of this angular momentum is constant. And if it is happening in this plane only, which is happening, then this angle is also means the direction of this unit vector is also the same. So this vector, angular momentum vector, is constant. Okay, so that's all for this video.